Hello. So today I'll be solving a few questions on HVL and TVL, that is half value layer and tenth value layer. Before that, let's just briefly understand what attenuation means, what transmission means. Attenuation basically just means that the photons which are stopped by the material transmitting material, and transmission is the photons that are transmitted across the material. So if this is the block of a material, if these are 10 photons, and if 10 out of the 10 photons, if 5 are attenuated and 5 are transmitted, these 5 are transmitted and the rest of the 5 are attenuated. Okay, this was 100% before, now it has become 50%, right? So that makes us half. That is the half value layer of the material, the thickness of the material, which makes the intensity of the photon, the number of photons, into half, is the half value layer. All right. So the next point is TVL. TVL is 10th value layer, the thickness of the material, which reduces 100% of the beam to 10% of the beam, making only the 10% to be transmitted and 90% to be attenuated, is 10th value layer, that is TVL. Now, so if you just go by this, if there is 100% of the beam, 1 HVL is needed for the beam to be attenuated to 50%, 2 HVLs for 25%, 3 HVLs for 12.5%, and 4 HVLs for 6.25, 5 HVLs 3.125, and for the sixth HVL it will reduce to up to 98%. So 6 HVLs are required for us to get into 97 to 98% of the uh, attenuation, and only 1.56% of the beam is transmitted. So a few quick formulas that are needed for us to solve those questions. This is HVL, the formula is ln 2 by mu. This is the linear um, attenuation coefficient, right? So ln 2, if you calculate, if you see, the value is 0.693, which also gives us this formula. And another formula to remember is 1 TVL equals 3.32 HVLs. Um, other um, other concept that we have to know before solving the questions is a polyenergetic beam and a monoenergetic beam. As the term suggests, polyenergetic means there are different kind of energies in the beam. There are low energies, there are high energies, and monoenergetic beam means all of the photons are having same energy. All right. So if you put a HVL, if you put a attenuating material, so the first HVL attenuates the lower energy beams, and the final beam will be a low energy filtered beam, that is hardened beam. That's why in a polyenergetic beam, the point that you have to remember is the second HVL is always greater than the first HVL. Now coming to monoenergetic beam, since the energies are similar, the HVL over here is always constant. So the second HVL is equal to the first HVL. All right. So uh, another few formulas that are needed is attenuation is n equals n naught into e to the power of minus mu x, where n is the final number of photons and 0 is the initial number of photons. Mu, as we know, is the linear attenuation coefficient, x is the thickness of the block, and another similar formula where n is the number of HVLs. You can remember this formula. So these are the basic points that are required for us to know before solving our questions. So let's start solving a few questions. The first question: which of the following provides the greatest amount of shielding? These are the four options: 10 HVLs of concrete, 6 centimeter of lead with a beam of HVL 12 mm, 2 HVLs of lead, 1 TVL of lead, and 1 TVL of concrete. So if we break this question down, for the first option, If there is 100% of the beam, after it passes 10 HVLs, the intensity of the beam is 0.0957 percentage attenuated. That's the transmitted beam. In the sense, so much of it is attenuated. The resultant one is 0.0975. For the option B, so if 1.2 centimeter is the HVL, then the total thickness is 6 centimeter, which gives us 5 HVLs. So 5 HVLs gives us 3.125. And the option C, TVL, where 100% is reduced to 10% with one TVL, and with another TVL, 10% is, 10% of the 10 is 1. So it reduces to 1. With option D, 1 TVL of lead and 1 TVL of concrete. Again, if you add both the TVLs, then it again reduces to 1. 100 to 10 and then 10 to 1 with 2 TVLs. Okay, so among the given options, the greatest amount of attenuation which is provided by option A. Right. The second question. Okay, if the linear attenuation coefficient of a photon beam is 1 per centimeter, the half value layer is, as we know, the formula is HVL is equal to 0.693 by mu, where mu linear attenuation coefficient is 1, then HVL will obviously be 0.693 by 1. The next question, the TVL, assuming there is no beam hardening, is, as we know, this is the formula, so the option over here is 3 to 4 HVLs. The next question, if the linear attenuation coefficient is 0.05, the HVL is, so if you put the same thing into the formula, we will get this as the answer. So the answer is E. Next question, which of the following statements about X-ray attenuation is true? The first option, mass attenuation coefficient of water and ice are different, is wrong because it is same. The linear attenuation coefficient of water and ice are same is again wrong because it is different. Option C, the second half value layer of a polyenergetic X-ray beam is greater than the first half value. So this is correct. Option D, second half value layer of monoenergetic beam is greater than first HVL is wrong because it is constant in monoenergetic beams. The next question, if 0.5 mm of lead attenuates an X-ray beam by 91%, 0.25 mm of lead will be expected to attenuate what percentage of radiation? So here, if the beam attenuates 91%, it is almost like it is attenuating 90% of the beam. So we'll assume that the TVL is 0.5 mm. So if you put that into the formula, the HVL which you will get is 0.5 divided by 3.32, which is 0.15 mm. So 0.15 mm is required for 50% attenuation. All right, so now they're asking 0.25 mm is for what? So 0.15 mm gets to 50% attenuation. So out of these options, this option is wrong, this option is wrong, this option is wrong because it is less than 50%. So among these two options, we know 90%, for 90%, uh, for uh, for 90% the TVL which was required is 0.5 mm. So the only option, for 99% the thickness that is required will be more than 0.5 mm. So the only answer which is for 0.25 mm is 70%. The next question, if the filtration of diagnostic X-ray beam is increased, the resulting beam will be, as we know, diagnostic X-rays are usually low energy, that is KV beam, and low energy or polyenergetic usually, and uh, when it passes through the first HVL, then the subsequent HVL needed will be more, and the dose rate will there will be a lower dose rate. So among the given option, the first option is correct. Coming to next question, the linear attenuation coefficient of the beam is 0.1 per centimeter. The HVL is, putting that into the formula, we will get 6.93 centimeters. Okay, the linear attenuation coefficient is always in centimeters, so a millimeter option is out. The next question. A narrow beam of megavoltage monoenergetic photons is incident on a water phantom. About 95% of the incident photons are transmitted through 1 centimeter of phantom. Approximately what percentage of originally incident photons will be transmitted after traveling through 2%? So with 1 centimeter of thickness, 100% of the beam becomes 95. Only 5% is attenuated. Okay, with another 1 centimeter, 95% of 95 is attenuated. So 95% of 95 is 90.25, which is approximately 91. That is option B. Next question. When a polyenergetic photon beam traverses a homogeneous material, the first half value layer is dash the second half value layer. So the first half value layer is always less than, because the second half value layer is greater than the first half value layer in polyenergetic beams. So the next question, how many TVLs are required to reduce the intensity of a beam by at least 95%? So with one, so they are asking about HVLs. With one HVL, we will reduce it to 50%, 25, then with third 12.5%, with fourth 6.25, and with fifth 3.125. So 4 HVLs reduces the beam to with 93.75 attenuation. With 5 HVLs, the beam is reduced to 96.85 attenuation. So at least 5 HVLs are needed to get at least 95 percentage of the intensity, to reduce the intensity to by at least 95%. The answer over here is D, 5. The next question is, half value layer is equal to dash of 10 dash 10th value layers. This is the formula. So if you give 1 by 0.332, which gives us 0.3 HVLs. So the answer over here is 0.3. The next question, approximate dose rate immediately outside a 3 TVL thick wall given a measured dose rate on the inside of the wall is 1000 centigrade per minute. So these are the 3 TVLs. There is inside of the wall, the dose rate is 1000, and they're asking just outside the wall what is the dose rate. Okay, with 1 TVL it is reduced to 110. With second TVL again it is reduced by 110, and the third TVL it is reduced by again 1/10. So 1 by 1000 divided by again 10 into 10 into 10, which again gives us 1. The answer is 1 by 1 centigrade per minute. So the next question is, the thickness of lead needed to reduce the exposure of a point source of 137 cesium by 70%, um, whose HVL is 0.65 centimeter, is dash. So they've given the half value layer, that is 0.65 centimeters. Now with that we can calculate the TVL, that is 2.15 centimeter. So with one HVL the dose is reduced to 50%, and the other HVL the dose is reduced to 25%. Totally, if you consider the attenuation, it is 75% attenuated. For 75% attenuation, 2 HVLs are required. 2 HVLs gives us 1.3 centimeter, which for they're asking for 70% attenuation. For 75% attenuation, it is 1.3 centimeter. So 70% attenuation gives less than 1.3 centimeters. Among the given options, these three is ruled out. Among these two, this is required for more than 75 percentage of attenuation. They're asking around 70, so I'll select these. Remember, these all of these questions can be solved by those attenuation formulas, but I wanted to keep it simplified so that we can solve these in exams. So with these simple steps we can solve. Otherwise we will have to have the calculator for E and log values. We can use the formulas also as well, but without the help of the calculator you can solve all of these questions in simple steps also. Um, the next question is the linear attenuation coefficient given a HVL of 0.693 is. So given again putting into the formula, we get that as 1. So the answer is B. The next question is what is the relationship between HVL1 and HVL2 for a polyenergetic KV photon beam? This is known. Polyenergetic photon beam HVL2 is more than HVL1. So option B is what it says. Next two questions are based on a graph. Um, so they have given this figure representing three different energy spectra for the next two questions. So let us understand this graph first. So on the x-axis there are photon energies, and on the y-axis there is intensity. So these are the low energy photons. As the energy increases, these are high energies. Okay, so here for the wave B, almost whole of the curve, almost all of the photons are of same energy in this curve, so it is monoenergetic curve. Okay, this curve curve A has both low energy and high energy photons, so it is polyenergetic. Even C has low energy and high energy photons, so again it is polyenergetic. But curve A has more of lower energy beams, and curve C has more of high energy beam. All right. So with this information, let's try to solve the two questions. So the first question is, which of the curve would be the first, for which curve would the first and second HVL be closest in value as the beams traverse a homogeneous material? So among A, B, C, these are the given options. As we know, for monoenergetic, the HVL 1 and 2 is almost same because it is constant. So the closest one will be B. For the second question, which curve would see the largest increase in HVL with low energy filter placed in the beam? So for option A, since we have more low energy beam, so the more of the lower energy beams, the second HVL, which is for the higher energy beams, will be much more compared to the HVL1. For the curve B, we know it is equal. For curve C, the HVL again will be more, but it won't be like the largest increase compared to curve A. So the answer over here is option A. So that's it for this. Thank you.